Okay, so now we're going to do an example problem. The example is 5-32 in the textbook. And for this problem, we are given that the velocity field is equal to a times cap u, both of which are constants, times y over x to the 1/2 power in the I hat direction, plus a times cap u, y squared over x to the 3/2 power, j hat, and cap a is equal to 141 meters to the minus 1/2 power, and cap u equals 0.24 meters per second. Okay, and we're to find A to show that V represents an incompressible flow. B, the acceleration of a fluid particle at x equals 0.5 meters and y equals 5 millimeters. C, the slope of the streamlines at x equals 0.5 meters and y equals 5 millimeters, basically at the same point as we did for point C. And I'm adding a part D, and that's the simplest function for u if v equals au y squared over x to the 3/2 power. Okay, for the flow to be incompressible. Okay, so now we know what we're given, and now we just need to solve the problem. So solution. Well, first for part A, recall that that the condition for incompressibility is that the divergence of the velocity vector is equal to 0, and that is the incompressibility condition. Okay, so to check if the flow is incompressible, we just need to stick in the velocity vector into and compute its divergence and see if it's equal to 0. So in 2D Cartesian, the divergence of the velocity vector is partial u, partial x, plus partial v, partial y. So here, for the velocity vector, we have u is equal to the I hat, the magnitude of the I hat component, which is a times cap u over y, x to the 1/2 power, and v equals a times cap u y squared over x to the 3/2 power. Oops, that's a bad half, so we'll just do it over here. Okay, so now all we do is we just stuff these in. We just stuff u and v into the partial derivatives and check if it's equal to 0. So doing that, we have partial x of u, which is a times cap u y over x to the 1/2 power, plus partial y, a u cap y squared over x to the 3/2 power. And we expand that out and we do these derivatives. These are pretty straightforward derivatives. This equals minus 1/2 a times cap u. Those are both constants. Y is not a function of x. And over x to the 3/2 power plus a over 2 u y over x to the 3/2 power. And you can see that these two cancel out, and this is equal to 0. So this implies that for the given velocity field, its divergence is equal to 0, which implies the flow is indeed incompressible. Okay, so we have basically proved that. Now, if the divergence of the velocity field was not equal to 0, the flow would be compressible. Okay, so that ends part A. And so if you're given a problem and you are asked to check if a velocity field is incompressible, all you need to do is just stick it in to the incompressibility condition here, and just check and substitute in the velocity components over here, and just check and make sure that it is equal to 0. If it's not equal to 0, then it is not an incompressible flow. Okay, so now moving on to part B. And for part B, we were to find the acceleration at a specific point. So first, recall that for in an Eulerian representation of a fluid flow, the acceleration vector is given by the substantial derivative of the velocity vector. Okay, and so that's cap d v dt. And so in 2D Cartesian, coordinates, the substantial derivative operator is given by d by dt acting on any variable, that's just any variable, is equal to partial of that variable with respect to time plus the x component of the velocity field times partial of the variable with respect to x plus the y component of the velocity field times partial of that variable with respect to y. Okay, and so if we want to find the acceleration, we apply this operator d by dt on the velocity vector. Okay, so A equals dv dt. That equals partial v partial t plus u partial v partial x plus v partial y. And now we substitute in the expressions for u, v, and the velocity vector. Okay. So we substitute them in, and this is going to be a bit lengthy here, and I apologize for that. That's just the way it is. And we have A equals partial t of a u y over x to the 1/2 I hat plus a u y squared over x to the 3/2 j hat plus a small u, which is a u y over that's a bad y, over x to the 1/2 times partial x of the velocity vector. Okay, and I'm going to cheat. And since I'm doing this on my iPad, I can just copy this. Like so. Okay. Plus v, which is a u y squared over x to the 3/2 power times partial y of the velocity vector. Okay. So here's our expression. We've just simply substituted in the velocity vector when it calls for the velocity vector, keeping careful to note that the I hat and j hats are always there, and substituting in small u, which is right here. And when we substitute in the small u, we do not include the I hat because small u is just the magnitude of the velocity component in the x direction, and similar for for small v, which is right there. So now we just take these derivatives like so, and notice that the velocity field is not a function of time. There's nothing here. There is nothing here that is a function of time. This means that the velocity field, if you recall, is steady. And so if the flow is steady, it's not a function of time, and the time derivative is 0. Okay, so I'll just fill this in a little bit. This is small u. This is the velocity vector. This is the velocity vector. And this is small v. Okay, so now we have already crossed out one term over here. Now we just do the partial derivatives as the calculus says to do. So then the acceleration equals a u y over x to the 1/2 times the x derivative of this function over here. And so that is minus 1/2 a u y over x to the 3/2 I hat minus 3/2 times a over 4 u y squared over x to the 5/2 power. Okay, j hat. So all I've done was I just took the x derivative of the velocity vector here. Okay, that is all I did. And now we have to add this term over here. So small v, which is a cap u y squared over x to the 3/2 times the y derivative of the velocity vector here. And so subbing that in and just doing the calculus there, that's a u au over x to the 1/2 power I hat plus 1/2 au y over x to the 3/2 j hat. Okay, and so you can combine these two terms and simplifying. We get that the acceleration is equal to minus 1/4 a squared u squared y squared over x squared I hat minus 1/4 a squared u squared y cubed over x cubed j hat. Well, there are a lot of common terms here, so we can simplify them out. So this equals minus 1/4. Oops. Or minus 1/4. We can factor out an a squared, u squared, y squared over x squared. Times a u y over x squared times I hat plus y over x j hat. And so that is what the acceleration in symbolic form is for this flow field. And now I'm not going to show the details, but if you sub in the numbers, that u equals 0.24 meters per second, a equals 141 meters to the minus 1/2 power, and this is at x equals 0.5 meters, and y equals 5 millimeters, which is equal to 0.005 meters. So if you substitute in these numbers, here into our equation that we derive for the acceleration, and you'll get that a equals minus 0.0286 meters per second squared I hat minus 0.000286 meters per second squared j hat. Okay, so that's our final answer for B. Okay, so now we're going to move on to part C. And so for part C, we're asked to find the slope of the streamlines. And recall from way back in lecture 1 or lecture 2 that in 2 dimensions, a streamline is defined by dy dx equals v over u. Okay, and so we know v and we know u, so we just simply substitute them in. So we have a u y squared over 4x to the 3/2 power. That's v. And now u is au y over x to the 1/2 power. Well, we can cross out most of these terms. And this implies that dy dx is equal to 1/4 y over x. Okay, and so this is the slope of the streamline. And so dy dx of the streamline at our given point equals 1/4 times y, which is 0.005 meters, over x, which is 0.5 meters, and implies that dy dx, or the slope of the streamline, is equal to 0.0025, and that's unitless. Right, because we have meters divided by meters, which is completely unitless. Now note, you could consider this as somewhat of a small review for stuff we did quite a while ago, that if the problem asked for the equation for the streamlines, we could certainly do that. If we wanted the streamlines, we'd have dy dx equals 1/4 y over x. And so here, and this is a differential equation now, and we can solve this to find the actual equation to compute the streamlines. So this is a nice first order separable ODE, and so we separate, and so this implies that dy over y equals 1/4 dx over x. Okay? So now we go and we go and integrate this, and this gives us ln y equals 1/4 ln of x plus some integration constant, and I'll just call that c1. Okay, and so we can exponentiate both sides, and so we have y equals e to the c1, and this is just a constant. Okay, and I'll just call that c, because e to the constant is just another constant, times x to the 1/4 power. So this implies that the equation for the streamline is given by y equals some constant, x to the 1/4 power. And recall that this constant is different for each streamline. So const is different for each streamline. Okay, and so for this flow field, the streamlines in the upper left quadrant would look something like this. Oops, x, y. Okay, and so this is what the streamlines would look qualitatively like. And again, given this velocity field, for the final, it wouldn't be a bad idea to know how to find the path lines and the streak lines given this velocity field too. Okay, and so now we're going to move on to the last part, part D. And so part D, we were asked to find the simplest allowable function for u for the flow to be incompressible. Okay, and so here we are going to pretend that we don't know u, but we know v. So here we know v equals a u y squared over x to the 3/2 power. And so want u such that the divergence of the velocity field is equal to 0. Okay, and spoiler alert, when you do this, you should get u is equal to the function given way up above in the problem statement. But here I'm showing you this step because there's going to be a homework problem that asks you to find the simplest function, and there are some subtleties into doing this because this divergence constraint here, it gives rise to a partial differential equation. And when you integrate it, you are integrating a function of a multidimensional function in just one direction only. Okay, and so there's some subtleties with that that I feel it's prudent to show you how to deal with. Okay, so we know v, and we want to find u such that the flow is incompressible or divergence free. So in 2D Cartesian, we have partial u, partial x, plus partial v, partial y. That's equal to 0. So we can't do anything with u yet, so that's partial u, partial x, plus partial y, y not x, of v, and that's a u y squared over 4x to the 3/2 power. Okay, and this has to equal to 0. Because again, we are finding u, we are finding a function for u to basically make the statement true. Okay, and so we take the y derivative of this, and substitute that. So we just have, this implies that partial u, partial x, plus a over 2 u y over x to the 3 halves a power is equal to 0. Okay, so now we rearrange this this equation here, and we have partial u partial x equals minus a over 2 u y over x to the 3 halves power. Okay, and so similar to the streamlines above, we now have what looks like a separable ODE, but there's a very subtle a wrinkle here, and that these are partial derivatives. Okay. And so u in general equals u of x, y, etc. Okay, and when we solve this essentially differential equation here, we are only integrating in the x direction. Okay, and so when we do that, we pick up no information about the y direction. So our constant of integration, when we do this integral here, when we actually integrate this, our integration constant, because we are only integrating for x but not y, our integration constant is actually can be a function of y. Okay, and so here's what I mean by that. So we integrate as you would normally, is you basically multiply both sides. We have partial u equals minus a over 2 uy over x to the 3 halves partial x, and you can simply integrate like you normally would. And if you do that, we have u equals the integral of minus a over 2 u y x to the 3 halves dx. Okay, but now there is an integration constant here that we need to deal with. And as I said before, this is only a statement. We are only integrating in the x direction only. So now our integration constant, as I said before, is not a constant, but it's a function of y. Okay, because again, you can take the partial derivative of this u function here, basically with respect to x, and it still equals, and it will still equal this. Okay, so now we just do this integral over here, and we have u equals minus a over 2 u y, because these are not functions of x, the integral x to the minus 3 halves dx plus f of y. So now we do that, and this implies that u equals minus a over 2 u y times minus 2, just performing this integral over here, minus 2 over x to the 1/2 power plus f of y. Okay, so just simplify this out, and we get that u equals a times u y over x to the 1/2 power, which this is the same, which so far this is the same as the problem statement, plus any function of y. Okay, and so in general, u is given by this function over here, where it is a times u times y over x to the 1/2 power plus any function of y only. Again, you can substitute this in and it will satisfy the incompressibility condition. But now the problem statement is asking for the simplest function of y. And what do you think the simplest function of y is? Well, that is in fact 0, which is the simplest function of y. And so the simplest function of y is no function at all. And so the simplest function, and so the simplest u, the simplest function for u that will satisfy the incompressible flow condition is u equals a u y over x to the 1/2 power. And this is the simplest u to satisfy incompressibility. Constraint. Okay. Okay, and so if you're given a homework problem and you're asked to find the simplest function of u or v or w to satisfy the incompressibility constraint, I expect you to show this step and basically argue that. Okay, and so that is it for this example here. Okay, and so before we're going to start to move on to conservation of momentum in the next recording, but I'm going to go over two quick things first. First, I'm going to just make a note on the meaning of divergence. Okay, these terms like curl and divergence are pretty formidable the first time you encounter them. And certainly for a lot of you, they're a relic of Calc 3 that you'd probably sooner forget. But in fluid mechanics and a lot of other areas, electrostatics and things like that, divergence and curl and things like that are actually extremely useful. So in the context of fluids here, we have a way to actually explain what that means physically. Okay, so recall conservation of mass. And that's given by partial rho, partial t, plus the divergence of rho v. And so this is equal to 0. And now we're going to assume if the flow field is smooth and differentiable, we can actually use a product rule on this divergence term here. And so here we're just going to use the identity. Note that the divergence of a scalar a times some vector v is equal to b dot grad a plus a times the divergence of b. So you could kind of think of this as a you can kind of think of this identity as a sort of product rule for the divergence of a scalar multiplied by a velocity vector. Okay, and so, but again, we can only do this if the product of a and b is a differentiable function. And as I said in a previous lecture, in fluid mechanics, quite often our rho, which is the scalar, and v, which is the vector, in many scenarios that is not differentiable. So this isn't so for those of you who wind up working in compressible flow and you deal with shock physics, in those situations, across a shock wave or something like that, rho v is not differentiable. And so you start dealing with this with the stuff, these sort of things that are mentioned in Calc 1, and you sort of forget about them. that you can only use the product rule if the function is uh, uh, if the function if that overall function is differentiable. Well, in very real applications, you cannot do things like that. So, but if we assume that the flow field is smooth and differentiable, we are assuming that you can use this vector identity on that. So if we use that with a is equal to rho and b is equal to the velocity vector, we have partial rho partial t plus rho times the divergence of the velocity vector. Oops, I did that backwards. I'll probably do it the other way around. Of the velocity vector dotted with grad rho plus rho times the divergence of the velocity vector, and that's equal to 0. Okay, and recall that d of a variable with respect to time is equal to partial of that variable with respect to time plus v dot grad of that variable. Well, here we have partial rho partial t plus, here we have partial rho partial t plus v dot grad rho. And so essentially here, this combination of variables is just d rho dt. Okay? And so applying that, we have d rho dt equals minus rho times the divergence of the velocity vector. I'm going to divide both sides by rho. So we have that 1 over rho d rho dt equals the divergence of the velocity vector minus the divergence of the velocity vector. So so far, this is looking like not too much here, but I'm just going to make a little quick change of variables. So note that rho equals 1 over, and I'll use it as sort of a funny curve v, and this is the specific volume. I don't know why in thermodynamics and fluid mechanics why they love the variable v to represent nearly everything. It wouldn't be too hard to make a problem that is incomprehensible because of all the v's that would be present in that. Okay, but at any rate, I'm going to substitute this into here. Okay, because sort of density is a sort of tougher thing to think about than a volume. And so I'm just going to turn this into a volume. And so, substituting that in, we have v times d 1 over v dt equals minus the divergence of the velocity vector. And we can basically use the chain rule on this, and I assure you that works in a very similar way to any other chain rule. So this equals, but I'm not going to prove it. This equals minus 1 over v squared dv dt. Okay, and so this equals, if you substitute this in, this equals minus v over v squared dv dt equals minus the divergence of the velocity. Well, we can basically cancel out the negatives and cancel out one of these v's. And so this means that 1 over v dv dt equals the divergence of the velocity vector. So, great, whoop-de-doo, what does this represent? Well, this means this here, this term here represents the fractional change of volume of a differential or infinitesimal, I should say, fluid element. Okay, and so this is saying, and so this expression here is literally saying that the fractional change, or you can think of it as the percent change of volume, is equal to the divergence of the velocity vector. And so for a compressible flow, we could think of, we have a circular control volume, and we have some sort of inward moving flow like this, and we track this control volume basically such that it is always around a fixed amount of mass. Well, for this type of flow, we can show that the divergence of the velocity vector is less than 0. And basically what that means is that the flow is basically moving inwards like this. And so as the flow is moving inwards, this control volume ring that you'd have to take is getting smaller and smaller and smaller. Okay, and so basically that change of volume is given by that change of volume is related to the divergence of the velocity. Okay, now if the flow is divergence free for an incompressible flow, which means that the divergence of the velocity field is equal to 0, that means that no matter how hard I push on our fluid element, its volume will basically never change. So you can think of if I have some sort of weird fixed geometry here, like this, and I have a glob of fluid over here that looks like this. And I have a glob of fluid for an incompressible flow, because the flow is divergence free, and because the flow is divergence free, we can say that if for an incompressible flow, we can say that that the velocity divergence is equal to 0, which means that the fractional change of volume is also 0. Okay, so this implies that 1 over v dv dt is also equal to 0, which implies that the change of volume is equal to 0. Okay, and so what this means is that, say I take my finger and I push the fluid into here, and so if I take my finger and I push the fluid over here, and I push it that way, what is going to happen is the volume cannot change. So in other words, that fluid is going to go spurting out. It's going to go spurting out of any hole that is basically there. So it's basically like those things that if you basically have this sort of blobby fluid, and I push inward on it here, it's going to move outward somewhere else. Okay. And also, one way that you can think of these incompressible fluids is they're not a solid, but you can sort of, in a theoretical sense, you can think of them of think of a incompressible fluid as having a Poisson's ratio of 0.5. Okay, now again, I'm not saying you could use solid mechanic like principles on a fluid, but you can think of how they behave. That if you push on one end of it, that if you compress one end of it, because the volume is not going to be that the volume cannot change. It's that it's just going to grow somewhere else. And so solids with a Poisson's ratio of 0.5 are behave just like that. And so actually, I think rubber is actually very close to that. And so basically, rubber is so solids that have a Poisson's ratio of 0.5 are sometimes called incompressible solids. Okay. And the last thing that I'm going to go over, if I can find my notes, is the rotation of a fluid element. Oops. Okay, I'm not going to spend too much time on this, but you could sort of, you could consider a velocity field with streamlines like the following, where the streamlines just basically form a bunch of circles. Okay, and so if we consider a fluid element at the very center, like this, and the circular streamlines, the fluid element at the center, and we have the circular streamlines. This fluid element is supposed to be at the exact center here, but of course my drawing skills are not very good, but that is basically what it is. You could imagine that basically what this fluid element is going to do, if the velocity field is basically right, is the square is basically just going to rotate and spin around in circles. And so the angular, I'm not going to do too much work with that here, but the angular of velocity is given by the curl of the velocity field. Okay? And so the curl tells you how fast a local region of the flow is spinning. Okay? And there is a property called vorticity, and that is traditionally given the symbol omega. It is a vector, and that is equal to 1/2 times the curl of the velocity vector. And so this is more commonly used. And so and this phrase vorticity, it is related to a vortex, which is just a region of spinning fluid. So a vortex is a region of spinning fluid. So if you want to calculate at any given location how much the fluid flow is spinning, you can actually just compute the vorticity. Okay? And so, but yeah, that should be fairly straightforward. You just need to look up the curl operator for a given coordinate system. Okay, and so for the previous example, you should be able to find the vorticity at the point 0.5 meters and 5 millimeters. Okay, so that's a fairly straightforward application of the curl. Okay, and just note that a fluid or a flow, I should say, not a fluid, is said to be incompressible if omega, or the vorticity, is equal to the zero vector, which this implies that the curl of the velocity vector is equal to the zero vector. So this is the flow is incompressible. Sorry about that. Irrotational. Okay. Okay, and then for those of you who have had aerodynamics, you know that that if the flow is incompressible, steady, has constant density. If the flow is steady, incompressible, and is steady, incompressible, and has constant density, and it's irrotational, you can use Bernoulli to relate any 2 points in the flow. Okay, and so if you have an incompressible flow that is irrotational, which that's actually fairly restrictive, you can use Bernoulli equation to relate any 2 points. Okay, and that is used in aerodynamics quite often. And these have a special name called potential flows. And there's a lot of really nice mathematical tools to analyze potential flows, and those are used to calculate the pressure forces and things like that acting on airplane wings, and they're used all the time. But in this class, we will not cover them. And so that's it for this lecture. For the next lecture, we're going to pick up and work with the differential form of the momentum equation, which is the Navier-Stokes equations.